Hi, my name is Xin Yi. I'm a PhD student from Washington University in St. Louis. Today, I'm going to present robust computation of implicit surface networks for piecewise linear functions. Implicit representation of geometry have been widely adopted in computer graphics. A smooth watertight surface, like this bunny, can be represented implicitly as a zero-level set of a function defined over the entire domain. Implicit surfaces are not limited to representing only smooth and solid shapes. Piecewise smooth and even non-manifold shapes can be modeled using not one, but a network of implicit surfaces. One way to define such a network is by intersecting multiple implicit surfaces. The resulting surface network partitions the domain into disjoint regions. The partition structure is often known as arrangement. Implicit arrangement is useful for modeling piecewise smooth shapes. This can be done using traditional CSG operations or using a graph optimization approach that we introduced in SIGGRAPH last year. The arrangement can also be used to model intersecting structures such as geological faults. Another type of implicit surface network is material interface, which partitions the domain into regions where one function is greater than all other functions. Each component of the material interface is actually the zero-level set of difference between a pair of functions, and therefore also an implicit surface. The material interface is perhaps the most widely used representation for shapes with interior partitions, such as multi-phase fluid, assembled mechanical parts, and anatomical structures. Like a single implicit surface, an implicit surface network is often discretized on a spatial grid, given function values at grid vertices. A common approach is to first compute the label at each grid vertex. For implicit arrangement, this label is based on the signs of the functions. For material interfaces, the label is a function with a maximal value. Then a polygonal mesh is created to separate vertices with different labels. While simple to implement, this approach cannot capture well a surface network that intersects with a grid cell in a non-trivial way, such as having more than two intersections at a grid edge. This limitation often leads to geometric and topological artifacts in discretization, particularly near narrow and thin features. As an example, consider a 3D material interface that contains a very thin region sandwiched between two hemispheres. A 2D cross-section is shown in this picture. A label separation method would typically fail to reproduce that thin region and instead created many fragmented regions. A more accurate approach for discretization is to extract the surface network from a piecewise linear interpolation of function values. This approach works on a simplicial grid, such as a triangular grid in 2D and tetrahedron grid in 3D. Because interpolating values at the grid vertices produces linear function within each grid cell. The linearity of the function greatly simplifies the structure of the surface network. For an example, the level set of 2D linear function is a line, so the implicit arrangement within a triangle consists of intersecting line segments. The material interface in a triangle is a convex polygonal subdivision. An intuitive way to understand this structure is by lifting each linear function to be a 3D plane. The material interface is a 2D projection of the upper envelope of the lifted planes. Similarly, for linear function interpolated within a tetrahedron cell, the implicit arrangement is formed by intersecting planar polygons, and the material interface is a convex polygonal subdivision. Compared with label separation methods, discretizing using piecewise linear interpolation offers significantly improved accuracy, particularly near thin features. In this example, the piecewise linear interpolation method creates a contiguous thin region sandwiched between two hemispheres. However, computing surface network of linear functions needs to compute intersection of planes. Such computation can be sensitive to numerical errors when the planes are close to being degenerate, such as when more than 3 planes almost intersect at a common point, or more than 2 planes almost intersect at a common line, or planes that are almost coplanar. Existing methods compute intersections in a non-exact manner, which may result in surface networks having a wrong combinatorial structure. Even worse, some algorithm may not be able to proceed if a key assumption fails due to numerical errors. In this paper, we propose new algorithm to discretizing implicit surface networks on a simplicial grid using piecewise linear interpolation. We'll adopt a unified approach for computing both the implicit arrangement and the material interface. Our algorithm guarantees to produce the correct combinatorial structure of these surface networks and can efficiently handle complex inputs containing dozens of functions. Our input is a tetrahedron grid, and each grid vertex is associated with a vector of function values. The core of our algorithm extracts the implicit surface network within each tetrahedron as a polygonal mesh. These per tetrahedron meshes are then connected to form a complete surface mesh, and finally we compute the partition of the space consisting of regions, patches, curves, and vertices, as well as their adjacency. This talk will focus on the first stage of the pipeline, where our main contribution lies. This is also the only stage where the algorithm for implicit arrangement and material interfaces differ. As mentioned earlier, given linear function defined within a tetrahedron, both implicit arrangement and the material interfaces are convex decomposition of the tetrahedron. We represent both decompositions as 3D cell complex and construct them incrementally by adding one function at a time. The addition of a function involves splitting a subset of cells by a plane, followed by possibly merging the cells if we are to compute immaterial interfaces. Here we illustrate the cell splitting step, which is used for constructing both implicit arrangement and material interface. Given a new function, we first compute the sign of the function at vertices of the cell complex. For material interfaces, we use the sign of the difference between a pair of functions. Edge connecting vertices with different signs are then split at the location of zero crossings, which we call the cut vertices. We then connect the cut vertices to form cut edges and split the face on which they lie. Note that since the faces are convex, each face has at most one cut edge. Finally, we connect the cut edges to form cut faces and split the cell in which they lie. Again, since the cells are convex, each cell contains at most one cut face. The correctness of our algorithm rests on the correctness of the signs. Incorrect signs may lead to surface networks with a wrong combinatorial structure. They may also create ambiguous configurations, such as a face containing multiple cut edges or a cell containing multiple cut faces, in which case the algorithm cannot proceed. To compute correct signs, one option is to perform all intersections and sign tests exactly. This would typically require the use of rational representation of vertex coordinates, which comes with a significant computational overhead. To avoid this overhead, we propose a new approach that computes signs exactly without actually using vertex coordinates. The key idea is to represent each vertex implicitly using functions and tetrahedron faces that it lies on. Using this encoding, we developed a novel predicate that determines the signs directly from the input function values at tetrahedron vertices. Neither the encoding nor the predicate use coordinates. The coordinates are computed only in the next stage of our pipeline when we produce the complete surface mesh. Our approach is inspired by plane-based point representations that have been widely adopted in recent literature. We first introduce our vertex encoding. Each vertex in an arrangement is the intersection of three planes, whether they are tetrahedron faces or the level sets of implicit functions. So each vertex can be encoded by three indices that points to these tet faces and functions. For example, a vertex on a tet edge is the intersection of two tet faces and the level set of one function. A vertex on a tet face is the intersection of one tet face and the level sets of two functions. Similarly, each vertex in the material interface can be represented by four integers, each pointing to a tet face or function. For example, a vertex on the tet edge is the intersection of two tet faces and the level sets of the difference between two functions. And the vertex on a TET face is the intersection of one TET face and the level sets of pairwise difference among three functions. Now that a vertex is encoded as the intersection of level sets, we want to present a simple method to determine its sign in another implicit function. Consider, for example, a point way on a triangle that lies at the intersection of the level sets of two functions, f1 and f2. Each function is defined using barycentric interpolation from a triplet of values at triangle vertices. We are interested in the sign of a third function, f3, at the point way. The sign can be determined by the signs of the determinants of two matrices, as shown here, which involve only values at triangle vertices. We call this predicate the barycentric predicate, and it's designed for geometry defined implicitly by barycentric interpolation. The predicates for intersection points of fewer or more level sets have similar forms. For material interface, we replace the function values in the matrices by differences between pairs of values. Please see the paper for details. To further speed up the computation, we pre-compute lookup table that store combinatorial structure of surface networks for a small number of functions. Here we show some example entries of our implicit arrangement lookup table for one or two functions. The entries are indexed by the function signs of TET vertices, and in some cases, predicate signs on TET edges. Please see the paper for details. Now we show some results. We start by evaluating the robustness of our incremental construction algorithm. We created a benchmark that includes 4 types of near degeneracy in a tetrahedron: planes almost coinciding at a point, line segment, a triangle, or quadrilateral. The benchmark contains 10,000 randomly generated instances for each degeneracy type. We run our algorithm on each instance twice with different ordering of functions, and we find that the algorithm produces the same combinatorial structure in each instance. This test indicates the algorithm can robustly handle such near degeneracies. Next, we compare the performance of our algorithm with an alternative implementation in SIGGRAPH. This implementation computes exact intersections by representing vertex coordinates in rational numbers. The test sets consist of 100 random instances of 1, 2, or 3 functions within a tetrahedron. Our algorithm, which is completely coordinate-free, runs about 100 times faster on average in each case. We now look at the performance of our entire pipeline. We use a synthetic input for implicit arrangements that consist of uniformly distributed spherical distance functions. The running time of our method increases almost linearly with the number of functions. Our method is a few times slower than label separation methods mentioned earlier. However, such methods tend to create geometric and topological errors where the level sets intersect, even for this synthetic input. An alternative approach for computing implicit arrangement is to first extract the level sets of each function and then compute their arrangement using robust algorithm. However, even with the latest mesh arrangement algorithm, this two-step approach is many times slower than our method. This is because the mesh arrangement algorithm needs to locate collision between meshes, which is a global operation. On the other hand, our algorithm only needs to work locally within each tetrahedron. Finally, we showcase some interesting examples that suggest possible applications of our method. This is the arrangement computed for implicit surfaces that define a mechanical object using constructive solid geometry. Again, our algorithm is significantly faster than computing mesh arrangements on individual level set surfaces. Our algorithm for computing the material interface can be used to construct generalized VORONOI diagrams, such as the diagram of lines. Here is an example diagram of 20 rotating lines. In summary, we presented a new grid-based discretization method for 2 types of implicit surface networks. Our algorithm can robustly compute the combinatorial structure under piecewise linear interpolation and can efficiently handle complex inputs. As part of our future work, we would like to explore further speed up using parallelization, ways to improve mesh quality of the results, and designing grid structures that can lead to better discretization of a given set of functions. Thank you for your attention, and we invite you to try out our code and data in our project page.